Oh, there was an exercise. I was saying there was an exercise from the previous session. However, it's very similar to this one, example 2. In fact, it's the same data set. It's not the same data set. It's the same variables, but the exercise had a very large data set. So let's do this one first. It's the adult data set. And this data set, even though it's called adult, what it reflects are income levels. So what we want to do is we want to predict income levels. And this is one of those data sets that comes with the A-Rules package. Okay, and Hansler is one of the developers of either the algorithm, or he's a heavy hitter in this because there are many papers that are written by him talking about a priori. So this data set essentially is U.S. Census Bureau data. This one is relatively small, 49,000 individuals. And we have a mix, as we'll see in the data set, of variables or predictors of income. Income is going to be our consequent on the right-hand side. We have a mix of demographic information and numeric information. So we're going to have to pre-process the data, which is a common theme with association analysis. And note this example talks about binary indicator variables. Essentially, all of these numbers for support, confidence, and lift come from pretty basic calculations tied to zeros and ones. But you can represent a 1 as a label, for example, like the gender male. That's also binary. They're either male or they're not male. So the data does not have to be represented literally as zeros and ones, but it has to be an either-or condition. It can't be a continuous variable, can't have a range, unless it's an ordered factor. You can have a range with an ordered factor, and we'll see some of that. Okay, so, but again, they're discrete levels. They're always discrete levels. Okay, so income in this case is just going to be small or large. It's going to be less than 50K US or more than 50K US. Okay, so we're going to concentrate more on the antecedent conditions. And so it's a large matrix. So we're going to create a sparse matrix, a sparse transaction matrix format, which cannot be viewed directly as rows and columns. And so let's do this. Okay, so first of all, we need to, well, we have A-Rules already. Load up the data. Notice you don't see it down here anywhere. Give it the data command, and then it's available. We can see it down here. It's a data frame, 49,000 rows, 15 variables. Now, there are also NAs. Here, let's pop it open. There's some NAs in here. Okay, we're going to create a sparse matrix with this before we process it. At this point, we can look at it. But if you go down, let's see if we can find a couple of them. There is some missing data. Here's one. Okay, so what that means is, although in this original data frame we have 15 variables, we have 15 columns, for each row, which is a person, some of those columns are going to be unavailable. They're going to be NA. So the length of each row will vary. You can do that. You can handle that with a priori, but what it does is when you're processing a rule, it will affect the generation of rules and also the application of rules, because you'll have missing values. You'll have antecedents that don't have the same number of rows for records, same number of columns. Let me show you. It's consideration, but we have visibility over that. Okay, so we process what are the dimensions. So we have 49,000 rows, 15 columns. We look at just the first 3 rows. It's really kind of messy data. We saw it on screen, and it was smaller so we could see it. But when you do express it like this to show up in the console, kind of hard to see. But there is a combination of names and numbers, and a better command to actually understand what's going on is the structure command. And so let's do that once quickly. Okay, now we can see what I'm talking about. So age is an integer. That's not going to work. This variable that they don't even describe is an integer. That's not going to work. Education number is years through school, I believe, an integer. Then we have the amount of capital gain or capital loss that each person has experienced, in integer, hours per week in integer. So we've got to do something about those integer columns at a minimum. And so what we do with this FNL, looks like final weight or something, FNLWGT, we get rid of it. We get rid of a couple of these right off the bat. One way you can delete a column that is in an existing data frame is just to assign the value null. That doesn't put empty cells in the column. It actually deletes the column from the data frame. Note a data frame and a list share characteristics. So this gets rid of the entire column. Get rid of it there. Get rid of education number because it's redundant. And so if we look at the structure of it again now, before we continue to pre-process it, we see that final weight and education number are gone, but we still have it. This is a separate variable. Education is an ordered factor. Okay, so this variable education number were redundant. We need to do something with these variables down here because they need to be categorical. Okay, so what we're going to do is for hours per week, for both age, hours per week, capital gain loss, we're going to use the cut function, which will take a numeric and it will assign values to levels that are defined by the cut levels. What does that mean? Well, let's take a look. It's very useful when you want to change the data type from either integer or double to categories. So, we're making them ordered. Note you can have a categorical variable that does not have order, like gender, male, female, but you can also have ordered categories. Somebody who graduated from high school is less than somebody who graduated from college, is less than somebody that graduated from a master's program. So we're doing that, and with age, we're just arbitrarily setting up categories 0 to 25, 25 to 40, 40 to 60. That can't be age. What is that? Oh, hours per week. Okay, so the hours per week, some people work as many as 168 hours. We're just setting up 1, 2, 3, 4 categories for that. For age, we're setting up a category young, which is 15 to 25, middle-aged, 25 to 45, senior, which would include me, 45 to 65, and old, which is 65 to 100. And then for the capital gain and loss, I see your question there. I'll get right to you. For the capital gain and loss, we're just going to say positive or negative. Actually, we're going to say none. If it's 0, if the capital gain or loss is 0, it's none. If it's negative, it's low. If it's positive, it's high. And note this defines the labels for the levels. Note we're using uppercase and lowercase to distinguish between capital gain and capital loss. Here's a question that says, are the final columns just the values of all possible permutations of the original variables transformed into factors? Well, I don't think they're really permutations. What it does, for each value, it replaces it with the category that's defined by this function. So somebody who had an age of, for example, 20, in that row, instead of saying 20, it will be replaced by a label that says young. So the entire column, any row in the column that had a value between 15 and less than 25 will now say young. So it's not permutation, it's just a straight replacement of a value. It assigns it to a category defined by this.